Every decision you have ever made might have created an entirely new cosmos. This is the startling premise of the multiverse, a foundational idea in modern cosmology that reshapes our place in reality. By the end of this journey, you will understand the competing blueprints for the cosmos and the evidence that makes them more than science fiction. We will investigate if our universe is one bubble in an endless cosmic foam, and whether every quantum possibility branches into a new world. How does the idea of infinite realities change your perspective on a single choice? The multiverse is not one single, tidy idea. It is a spectrum of possibilities, a family of theories that all share one radical core proposition. Our universe, with all its hundreds of billions of galaxies, might be just one component of a far vaster and more complex reality. This is a profound shift in perspective. We are not talking about distant galaxies in our own cosmos, but entirely separate cosmic domains, each potentially operating under a different set of fundamental rules. In one domain, gravity might be a crushing force, making life impossible. In another, the nuclear forces that bind atoms together could be so weak that matter itself never coalesces. These are not different places in our space, but different realities within a grander meta-reality. This concept directly confronts a cornerstone of modern science, the Copernican Principle, which insists we do not occupy a special place in the cosmos. Yet if our universe is just one among countless others, its laws appearing perfectly tuned for our existence, then our cosmic address is not special at all. It is simply the one domain where the conditions were right for us to be here to observe it. This redefinition of reality itself raises an immediate and formidable challenge. If these other universes are truly separate with their own space and time, how could we ever find evidence for them? The answer begins with the first compelling blueprint for this cosmic architecture, a theory born from our most successful description of the universe's explosive beginning. Our universe may have been born in a single, explosive moment of creation, but what if that moment never truly ended? The theory of cosmic inflation suggests that a fraction of a second after the beginning, reality underwent a growth spurt of unimaginable speed, expanding faster than light itself. While this inflation smoothed out our local cosmic neighborhood into the universe we see, some versions of the theory propose it was eternal. In this grander picture, the inflationary process only stops in isolated pockets. Each region where it ceases becomes a separate bubble universe, floating within a still inflating background. Our entire cosmos, with all its hundreds of billions of galaxies, could be just one such bubble in an endless, frothing sea of new realities. Each of these cosmic bubbles inherits its own unique properties from the random quantum fluctuations that seeded its birth. The most crucial property is its vacuum energy, a fundamental energy permeating empty space. In our bubble, this energy is incredibly small but positive, which drives the accelerated expansion we call dark energy. In other bubbles, this value could be vastly different. A bubble with a much higher vacuum energy might expand so violently that matter is ripped apart before it can ever form stars or planets. Another bubble might have negative vacuum energy, causing it to collapse back in on itself in a cosmic crunch almost instantly after it forms. Only in rare bubbles, like perhaps our own, is this energy value just right for galaxies to coalesce and for life to eventually emerge. This elegant framework provides a potential answer to one of the deepest mysteries in physics, the problem of fine-tuning. Why do the fundamental constants of nature seem perfectly calibrated to allow for our existence? If an infinite variety of bubble universes exist, each with different laws, then it is no surprise we find ourselves in one of the few that can support us. The theory is not merely a philosophical speculation, but a natural, and for some physicists, an unavoidable consequence of our best models of the early universe. Yet a cosmos of disconnected bubbles presents a profound challenge. If we are trapped inside our own bubble, forever separated from others by an ever-widening gulf of inflating space, how could we ever hope to find evidence for our cosmic neighbors? The answer may lie in the faintest of echoes from our own bubble's violent birth. A collision between universes would be among the most violent events conceivable. If our cosmic bubble once brushed against another, the energy released would have sent shockwaves through the fabric of our newborn reality. The most promising place to look for the scars of such an encounter is the cosmic microwave background, the ancient afterglow of the Big Bang that paints the entire sky. This faint radiation is a snapshot of the universe when it was just 380,000 years old, and any major disturbance from that era would be frozen within its subtle patterns. Researchers analyzing data from the Planck satellite have searched for the specific signature of a bubble collision, which might appear as a distinct circular imperfection or a strange gradient of hot and cold spots that defies standard explanations. It would be a cosmic bruise, a faint but permanent reminder that we are not alone in the greater meta-reality. The hunt is incredibly difficult, requiring scientists to sift through vast amounts of data and rule out countless more mundane possibilities. So far, no definitive collision signature has been confirmed, yet the search itself is profound. It transforms the CMB from a simple relic of our past into an active crime scene, a canvas where we might one day find the fingerprint of a neighboring cosmos. This direct, observational approach makes the inflationary multiverse more than a philosophical idea. It makes it a testable scientific hypothesis. But what if the true architecture of the multiverse is not written in the vastness of space, but in the bizarre, probabilistic heart of reality itself at the quantum level? While we search the cosmos for the scars of distant bubble collisions, another theory suggests that new realities are being born not in far-off space, but in every moment right here. This idea emerges from the bizarre and counterintuitive world of quantum mechanics. At the quantum level, particles exist in a blur of possibilities, a state called superposition, where an electron can be in multiple places at once until it is observed. The traditional explanation for why we only see one definite outcome is that the act of measurement collapses this wave of possibilities into a single reality. But the many worlds interpretation proposes a radically different solution. It suggests the wave function never collapses. Instead, at the instant a quantum event occurs, the entire universe splits, branching off into multiple, equally real copies. In one branch, the electron is detected spinning up. In another, newly created branch, it is spinning down. Both outcomes happen, but in separate, non-communicating timelines. This branching is not limited to particles in a lab. It applies to every quantum event everywhere. Every time a radioactive atom decays or does not decay, the universe divides. Every time a photon takes one path or another, reality forks. And because your brain, your thoughts, and your choices are ultimately made of these quantum components, the implications are staggering. For every decision you have ever faced, a version of you exists in a parallel reality who made the other choice. A version of you turned left instead of right, took that job offer, or never even clicked on this video. This is not science fiction speculation, but a direct, if mind-bending, consequence of one of our most rigorously tested physical theories. The many worlds interpretation elegantly sidesteps the famous measurement problem in quantum mechanics. the puzzling question of why observation forces a definite outcome. It removes the special role of the observer, proposing instead that all possible outcomes are equally real. Yet this solution comes at an extraordinary cost, the continuous creation of an incalculable number of new universes. This raises a profound challenge for the scientific method. How can we test a theory that predicts an infinite number of realities that we can, by definition, never interact with or observe? If a theory explains everything by saying that every possible thing happens somewhere, can it ever be proven wrong? This question of falsifiability lies at the heart of the debate, pushing physicists to explore whether there could be a middle ground, a multiverse model that is vast but not quite so infinite. The idea of infinite branching worlds is a breathtaking vision, but it leaves a crucial question unanswered. Where do all these different sets of physical laws actually come from? String theory, a leading contender for a final theory of physics, offers a possible answer, and it is an answer of almost incomprehensible scale. This theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably small, vibrating loops of energy. The specific vibration of a string determines whether it manifests as an electron, a quark, or a particle of light. To make the mathematics of this theory work, it requires more than the 3 dimensions of space and 1 of time that we experience. It needs extra, curled-up spatial dimensions so tiny that they are forever beyond our direct perception. The true shock comes from the number of ways these extra dimensions can twist and fold upon themselves. The mathematics does not point to one unique solution, but to a staggering array of possibilities, a number so vast it defies analogy. This is the string theory landscape, a cosmic catalogue of potential realities numbering 10 to the power of 500 or more. Each entry in this catalogue represents a stable configuration, a unique universe with its own, unchangeable set of physical laws and constants. In one such universe, the strength of gravity might be 1,000,000 times stronger. In another, the electromagnetic force could be too weak to form atoms. Our universe, with its seemingly perfect balance for complexity and life, is just one single, specific entry in this near-infinite list. This landscape provides a potential physical mechanism for the inflationary multiverse, where each bubble universe is a different point in this vast topography of possibilities. It seems to offer an elegant solution to the fine-tuning problem. With so many options available, it is no wonder that at least one universe ended up with the right numbers for us to exist. Yet this vastness introduces a new and profound puzzle. If the landscape of possible universes is so unimaginably large, what selected our particular point from the cosmic catalogue? Does the existence of this landscape truly explain why our universe is the way it is? Or has it merely relocated the mystery to a different, even more abstract plane? The search for an answer pushes scientists to look for any faint trace, any subtle signature, that could connect this grand theoretical architecture to the reality we can actually observe and measure. If every possible universe exists, then our presence here is no longer a cosmic mystery. It becomes a simple, statistical inevitability. This line of reasoning is known as the Anthropic Principle, a powerful but deeply controversial idea. It works like a cosmic selection effect. Imagine you are a fish that has always lived in a pond. You might marvel at how perfectly the water is suited for your gills, its temperature and chemistry ideal for your existence. But of course it is. If the pond were different, you would not be there to observe it. In the same way, we could only ever find ourselves in a universe whose fundamental constants allow for stars, planets, and ultimately, life. In a multiverse of infinite variety, our universe is not special. It is simply the one that selected us. This perspective offers a powerful rebuttal to the argument for a cosmic designer. The universe is not finely tuned for life. It is one of the very few, rare corners of a vast reality where life was even possible. Yet this explanation leaves many scientists deeply unsatisfied. Does it truly explain anything, or has it simply relocated the question? Critics call it a cop-out, a philosophical sleight of hand that makes the multiverse theory immune to falsification. After all, if any possible observation can be explained away by saying it was necessary for us to be here, then what could ever prove the theory wrong? This is the central challenge: for the Anthropic Principle to be scientifically useful and not just a philosophical curiosity. It must be capable of making concrete, testable predictions. Can it tell us something specific about the universe we should expect to see? Surprisingly, it might. If our universe is just one among many hospitable ones, its properties should be typical of life-permitting worlds, not exceptionally ideal. For instance, the amount of dark energy in our cosmos appears strangely small. An anthropic prediction suggests that if we could measure the dark energy in all life-friendly universes, our value should fall somewhere in the middle of that range, not at an extreme end. Too much dark energy and the universe expands too quickly for galaxies to ever form. Too little and the cosmic structures might be too sparse. Our measured value, while tiny, seems to sit in that Goldilocks zone. This is a fragile but real attempt to turn a philosophical observation into a quantitative scientific tool. The debate over anthropic reasoning forces us to confront the very nature of explanation itself. Are we content with a universe that is merely one address in a near-infinite cosmic city, or does the human drive for understanding demand a unique, fundamental story for our home? This question pushes at the boundaries of science and philosophy, leading us to the final and most speculative frontier of multiverse theory, a place where the distinction between mathematics and physical reality begins to completely dissolve. The ultimate architecture of reality might not be physical at all. Beyond the bubbles and branching worlds lies a theory so fundamental it suggests the cosmos is built not from matter or energy, but from mathematics itself. This is the mathematical universe hypothesis, a vision where every consistent mathematical structure is a real, physical universe. Our cosmos, with its galaxies and laws, is not merely described by the equations of physics. It is one specific, incredibly complex equation. A universe where the rules of basic arithmetic hold true would exist. A universe governed by the strange geometries of hyperbolic space would be equally real. The multiverse, in this view, is the complete and unbounded library of all mathematical possibilities. We are self-aware substructures within one particular volume of this cosmic library, a volume complex enough to contain consciousness. This is a radical form of Platonism, proposing that the world we perceive is a shadow cast by a deeper, truer realm of mathematical forms. The elegance of this idea is profound, resolving the age-old mystery of why mathematics is so unreasonably effective at describing the physical world. The answer is simple: the physical world is mathematics, yet this breathtaking simplicity introduces its own deep puzzle, often called the reality problem. If our universe is purely a mathematical structure, why does it feel the way it does? Why do we experience the vibrant red of a sunset, the sensation of warmth, or the feeling of wonder? These qualia, these raw fields of conscious experience, seem entirely alien to the cold, abstract symbols of a mathematical equation. How does a set of axioms produce the taste of chocolate? This is the hard problem of consciousness, and it finds a stark new form within the mathematical universe hypothesis. Bridging this gap between abstract structure and tangible sensation may require a shift in perspective, focusing not on the mathematics itself, but on the information it processes and the observers that emerge from it. Perhaps the most profound challenge to our intuition comes from the study of the most enigmatic objects in the cosmos. The holographic principle emerged from a deep puzzle about black holes and the nature of information. Theoretical work revealed that all the information describing everything that falls into a black hole is not lost within its volume, but is somehow encoded on its two-dimensional surface, the event horizon. It is as if the three-dimensional reality inside the black hole is projected from a flat cosmic film. This startling idea was then generalized into a radical proposal, the holographic principle, which suggests that this could be a fundamental property of reality itself. The entire universe, with its vast three-dimensional richness, might be a holographic projection from a distant two-dimensional surface. We and everything we see would be incredibly detailed and complex shadows cast from the edge of space. If this is true, it implies a form of multiverse built not on branching timelines or cosmic bubbles, but on information. Different universes could simply be different projections, different ways of reading the same underlying code from the lower dimensional boundary. Think of a single complex barcode that can be scanned to produce many different, fully immersive virtual worlds. The core reality would not be the worlds themselves, but the information that generates them. This directly challenges our most basic classical intuition. We feel that we live in a solid, three-dimensional world, but this principle suggests that this volume, this depth, is an emergent illusion. Reality at its most fundamental level may not be made of particles or fields, but of bits of information. This informational multiverse raises a haunting question about the nature of the other projected worlds. If our universe is one specific projection, what are the others like? They would not be separate places in a larger space, but alternative renderings of the same foundational data. They might operate under completely different physical laws, not because their fundamental constants are different, but because the projection code itself is different. One projection might create a universe with 4 spatial dimensions we could never perceive, while another might generate a reality where time flows in multiple directions. The strangeness of quantum mechanics, with its particles being in multiple states at once, could be a natural consequence of this underlying informational architecture. The fuzzy probabilities of the quantum world might simply reflect the data processing happening on the cosmic boundary. This concept forces us to confront the absolute limits of our current physical theories. It suggests that space and time are not the fundamental stage upon which the universe plays out, but are themselves emergent properties, secondary to the flow of information. The holographic principle is not yet a complete theory, and finding direct experimental evidence for it remains a monumental challenge for physicists. Yet it represents a dramatic shift in our quest to understand the cosmos, pointing toward a reality where the code is more real than the world it generates. As we push our understanding to these extreme frontiers, we are compelled to ask if the search for a single, ultimate theory of everything is itself a kind of illusion, a beautiful dream that dissolves when we look too closely at the fabric of reality. Our own universe might be a three-dimensional island adrift in a far vaster, higher-dimensional ocean. This is the startling vision of Brane cosmology. The term Brane is simply short for membrane, and in this framework, our entire cosmos is one such membrane, a vast, flat surface with 3 spatial dimensions, existing within a background space that has more dimensions than we can perceive. This bulk space could be home to other branes, other cosmic islands floating parallel to our own. Each one would be a complete universe, potentially governed by a different set of physical laws, yet they could be separated from us by a gap so tiny, in a direction we cannot point to, that they remain forever invisible. This is not science fiction, but a serious extension of string theory, offering elegant solutions to some of our deepest cosmic puzzles. For instance, the mysterious dark matter that influences the motion of galaxies could simply be the gravitational pull of ordinary matter residing on a nearby parallel brane, its matter invisible to us but its gravity subtly leaking through. Even the Big Bang, the singular beginning of everything, might be reinterpreted not as a moment of creation from nothing, but as a violent collision between two of these cosmic membranes in the higher dimensional bulk. The most tantalizing possibility, however, involves a unique property of gravity. While all other forces, like electromagnetism, might be firmly trapped to the surface of our brane, gravity, which is the curvature of space itself, could be the one force that permeates the entire higher dimensional bulk. If this is true, then the gravity we feel in our universe could be subtly diluted, weaker than expected, because part of its influence is spilling over into other dimensions. This would explain why gravity is so astonishingly feeble compared to the other fundamental forces. Think of a laser pointer shining on a wall in a dark room. The light is concentrated on a single spot, but if that same light were a dim bulb illuminating the entire room, its intensity on any one part of the wall would be far weaker. Our universe could be that wall, and gravity could be that dim bulb, its strength diffused across the higher dimensional space. This provides a potential experimental path forward. Physicists are searching for tiny deviations in the force of gravity at microscopic distances, where this leakage into other dimensions might become detectable. The search is for a hidden signature of our cosmic neighbors, not in the distant heavens, but in the most delicate laboratory experiments on Earth. This debate strikes at the very foundation of how we define science. For an idea to be considered truly scientific, it must be falsifiable, meaning it must make predictions that could, in principle, be proven false by an experiment or an observation. The multiverse concept is often criticized for failing this fundamental test. If these other realities are permanently and completely disconnected from our own, sealed off by the inflationary expansion of space or the branching of quantum timelines, then how could we ever gather evidence to confirm or deny them? Critics argue that without this possibility of disproof, the multiverse slips from the realm of empirical science into the domain of metaphysics or even philosophy. It becomes a beautiful story, but one that is ultimately untestable and therefore, in a strict sense, unscientific. Proponents of the multiverse offer a compelling counterargument. They suggest we are not testing the other universes directly, but rather the underlying theories that inevitably predict their existence. Cosmic inflation and the many worlds interpretation of quantum mechanics are not fringe ideas. They are serious, well-developed frameworks that attempt to explain the observable features of our own cosmos. The multiverse, in this view, is not the theory itself, but a consequence of these theories. If our best models of the early universe and the quantum realm naturally lead to a multiverse as their outcome, then to dismiss it is to ignore a key prediction of the science. The search then shifts. We may never visit another universe, but we can look for the subtle, indirect footprints they leave on our own. The hunt for circular patterns in the cosmic microwave background is one such effort, a search for the cosmic bruise of a long-ago bubble collision. In particle physics, certain properties of the elusive Higgs boson could hint at the vast landscape of possibilities predicted by string theory. Even the inexplicably small value of dark energy in our universe can be seen as indirect anthropic evidence, suggesting our cosmos is just one among many. The challenge lies in interpreting this evidence. A strange pattern in the CMB might be a sign of a bubble collision, or it could be a statistical fluke, a mere random fluctuation. How do we know the difference? This is the delicate line scientists must walk, navigating between groundbreaking discovery and untestable speculation. The question forces us to reconsider the scientific method itself. Must every component of a theory be directly observable, or can we accept the existence of entities we can never see if they provide the most powerful and coherent explanation for the reality we can measure? The debate over the multiverse is not just about the architecture of reality. It is a profound conversation about the limits of human knowledge and the very rules of the game we call science. The delicate balance of our cosmos can feel like a miracle. Tweak the strength of gravity by just 1%, and stars would burn out in a cosmic flash, never giving planets the stable light they need. Adjust the mass of a single type of quark, and atomic nuclei would never form, leaving the universe a barren soup of fundamental particles. This apparent fine-tuning of nature's constants is one of the most profound puzzles in all of science. It seems as though our universe was crafted with life in mind, a notion that has fueled philosophical and scientific debate for generations. Yet within the framework of the multiverse, this cosmic perfection loses its miraculous quality. If an infinite array of universes exists, each with its own random set of physical laws and constants, then a universe like ours is not a statistical impossibility, but a statistical inevitability. We do not inhabit a universe that was finely tuned for us. We simply inhabit one of the rare, habitable corners of a much vaster reality. This perspective reframes our existence from a targeted event to a cosmic selection effect, much like a lottery winner marveling at their luck while ignoring the millions of other tickets that lost. But does this truly solve the mystery, or does it merely push it back a step? Skeptics argue that invoking an infinite number of unseen universes to explain the one we see is not an explanation at all, but a philosophical retreat. It replaces the question of why our constants are so perfect with the equally perplexing question of why a multiverse generator would spit out such a vast array of possibilities in the first place. The debate then turns to a deeper longing, a hope that there might be a single, elegant theory of a single universe, one that uniquely predicts the constants we measure without needing an infinity of failed experiments. The multiverse explanation for fine-tuning stands as a powerful, yet deeply contested idea, forcing us to weigh the nature of explanation itself against the staggering implications of a reality without end. An infinite multiverse presents a paradox at the heart of prediction. If every possible event occurs in some universe, and there are infinitely many of these universes, then how can we ever say one outcome is more likely than another? This is known as the measure problem, a deep mathematical challenge that questions the very meaning of probability in a cosmos without end. Think of a vast ocean with an infinite number of waves. You want to know if a wave is more likely to be large or small. But if the ocean is truly infinite, there are infinitely many large waves and infinitely many small waves. Comparing these two infinities seems impossible, yet our entire scientific method is built on calculating odds. This dilemma becomes intensely personal within the many worlds interpretation of quantum mechanics. In a constantly branching reality, there is no single original version of you. There are only countless copies, each following a different decision path. So what is the probability that you are the one who started watching this video, and not a copy who began a moment later? In an infinite ensemble, the question may be meaningless. For the inflationary multiverse, the problem is just as severe. If most bubble universes are barren, lifeless voids, but there are infinitely many of them, and there are also infinitely many life-friendly bubbles like ours, how can we calculate the expected odds of finding ourselves in a habitable cosmos? Without a way to count these infinite sets meaningfully, the theory struggles to make a firm, testable prediction about what we should observe. Solving this requires finding a mathematical ruler, a measure, to cut the infinite down to a size we can comprehend. Researchers explore this by considering only the finite regions of the multiverse accessible to an observer over a finite time, or by looking for a natural cutoff point in the physics. This is not just abstract philosophy. It is the hard, technical work needed to tether a breathtaking cosmic vision to the solid ground of scientific evidence. The very reality we experience may depend on how we learn to count the uncountable. Our everyday reality feels solid and singular, a stark contrast to the quantum blur of possibilities. The bridge between these two worlds is built by a subtle but powerful process called quantum decoherence. When a single particle exists in a superposition, it is isolated, its multiple potential states delicately connected. But the moment it interacts with its environment, everything changes. A single photon bouncing off the particle, a stray air molecule colliding with it, even the faint pull of gravity, these countless interactions act like a form of cosmic noise. They scramble the delicate phase relationships between the different branches of the wave function, effectively erasing any trace of interference between them. The branches do not vanish, they simply lose their ability to influence one another, becoming independent and parallel histories. This is why you never see a cat that is both alive and dead. The animal is never in a true superposition in the way a single atom might be, because it is instantly and continuously measured by its environment. Its possible states decohere almost immediately, branching into separate, non-communicating streams of reality. In the many worlds picture, you do not physically rip in two. Instead, your own conscious awareness, which is part of that environment, becomes inextricably correlated with just one of these decohered branches. You follow one thread of the narrative, completely unaware of the other stories unfolding alongside your own. This process transforms a single, universal wave function into the palpable illusion of a unique and definite classical world. Yet this elegant explanation leaves one profound mystery untouched. Why do we have a single, continuous stream of consciousness at all? Why does your awareness feel locked to one specific branch, experiencing a linear sequence of events, when the underlying physics suggests all possibilities are equally real? This question pushes beyond the boundaries of physics into the deep philosophical puzzle of how subjective experience emerges from an objective, branching reality. The quantum world presents us with a profound puzzle. We are told that particles exist in a haze of possibilities, yet our own experience is one of definite reality. The traditional explanation, known as the Copenhagen interpretation, places a mysterious power in the act of observation. It suggests that the wave function, this cloud of potential, collapses into a single, solid fact only when it is measured. This idea inevitably elevates the observer, and by extension consciousness itself, to a central role in the very fabric of reality. It is as if the universe remains a set of unfinished blueprints until a conscious mind looks at it, forcing it to choose a final form. This notion has captivated philosophers for generations, but it leaves many physicists deeply unsettled. Why should consciousness have such a unique, almost magical, power over the physical world? The many worlds interpretation offers a dramatic escape from this dilemma. In this view, there is no special moment of collapse. The observer is not a director who stops the show, but simply another actor on the stage. When a quantum event occurs, the observer becomes entangled with the outcome. Their own physical state, including the neurons in their brain that record the event, branches along with the particle. One version of you sees the electron spin up, while another, equally real version sees it spin down. Consciousness does not cause the split, it simply rides along, a passenger on one of the countless branching paths. This is a powerful simplification, removing the need for a magical line where quantum possibility becomes classical certainty. Yet this elegant solution introduces its own strange question. If all branches are equally real, what determines the specific stream of consciousness you are experiencing right now? This is known as the preferred basis problem. Why do you feel yourself to be the version of you that started watching this video, and not one of the infinite other versions who made a different choice a moment ago? The theory suggests that all these yous exist, each with an equally valid claim to being the original. Your sense of a single, continuous self may be an illusion, a local perspective within an unbounded cosmic narrative. The multiverse, in removing consciousness from a position of power, forces us to confront a deeper mystery about the nature of subjective experience itself. This leads us to a fundamental query. In a universe that is quantum at its core, what exactly qualifies as an observer? Is it a human being with a complex brain, a cat, a single-celled organism? Or perhaps even a simple particle detector? If we define an observer too broadly, then the specialness of consciousness vanishes, but the collapse of the wave function would be happening constantly, everywhere. If we define it too narrowly, we are left wondering how a physical process like measurement can depend on something as elusive as awareness. The multiverse frameworks sidestep this entire debate by doing away with the collapse altogether. An observer is just a physical system that becomes correlated with a quantum state, its information forever branching into parallel storylines. The vibrant red you see in a sunset, the warmth you feel, these are not causing reality to snap into place. They are the rich, internal experiences of one specific branch in an endlessly dividing tree of possibility. The drama of observation is not about forcing an outcome, but about which thread of the vast cosmic tapestry you happen to be woven into. Perhaps the most unsettling blueprint for reality suggests our cosmos is not a fundamental entity, but a generated one. The simulation hypothesis proposes that everything we know, from the farthest galaxy to the feeling of sunlight on your skin, is part of an immensely complex computational model running on a computer in some more fundamental, base reality. In this view, the programmer is not a deity but a technologist, perhaps a future human or an advanced alien civilization, and our universe is their creation. This idea shares a deep structural similarity with the multiverse. Just as the inflationary model predicts countless bubble universes, a civilization with such technology might run not one, but a vast ensemble of simulations, each with its own initial conditions and programmed laws of physics. The multiverse, in this scenario, is not a frothing sea of cosmic bubbles, but a server farm of virtual worlds. While this might sound like the plot of a science fiction film, some philosophers and physicists argue we must take the possibility seriously. If a civilization could ever reach the technological stage where creating realistic universes is possible, then the number of simulated realities would quickly and vastly outnumber the one base reality. Statistically, we are more likely to be living in one of the countless simulations than in the original world. This line of reasoning is known as the simulation argument, and it forces a stark choice. Either intelligent civilizations never reach such a technological peak, perhaps self-destructing first, or they choose never to run such simulations, or we are almost certainly living in one right now. To move this from pure philosophy towards science, researchers have considered what fingerprints a simulation might leave in our reality. A programmer, even an advanced one, might take computational shortcuts. Just as a video game only renders the parts of the world a player is currently looking at in full detail, the laws of our universe might reveal similar approximations if we look closely enough. Physicists have proposed searching for evidence of a fundamental resolution to space-time, a pixelation of reality at the smallest possible scale. Others have looked for odd glitches in the distribution of the highest energy cosmic rays, which could be a sign that the simulation's code has a finite capacity for processing extreme events. So far, no such evidence has been found. The laws of physics, as we currently understand them, appear smooth and continuous down to the tiniest scales we can probe. Yet the search itself reframes our quest for a final theory. Could the ultimate laws of nature be more like the source code of a universe, a set of elegant algorithms that generate the rich tapestry of our experience? This computational perspective challenges our most basic intuitions about what is real. It suggests the architecture of the multiverse may not be built from space and time, but from information and processing power, a cosmic engine whose nature we are only just beginning to glimpse. A mysterious drift on a cosmic scale challenges the very idea of an isolated universe. In 2008, astronomers were mapping the expected motions of distant galaxy clusters, each one a colossal metropolis of gravitationally bound stars. According to the standard model of cosmology, these clusters should be moving in a random, chaotic dance, their individual velocities cancelling out to produce no overall direction on the largest scales. Yet the data revealed something profoundly unexpected. A significant number of these clusters, billions of light-years apart, were all streaming in the same direction at astonishing speeds of nearly 2 million miles per hour. This coherent motion was so vast and so strange that researchers dubbed it the dark flow. It was as if an invisible, cosmic river was pulling these islands of galaxies along a current that the known universe could not explain. One of the most provocative hypotheses to account for this phenomenon pointed directly to the multiverse. Perhaps the dark flow was not caused by anything within our observable cosmos, but by the gravitational tug of an immense concentration of mass in a neighboring universe, a cosmic structure lying just beyond the veil of our cosmological horizon. Think of it like feeling a breeze from a door you did not realize was open in a sealed room. The pull from that other realm would affect everything on our side of the boundary, creating a coordinated drift that our local physics could not generate. This interpretation was, and remains, highly speculative. The initial findings were met with intense skepticism, and later analyses with more precise data have cast serious doubt on whether the dark flow is a real phenomenon or a subtle systematic error in the measurements. Yet its story is profoundly important. For a brief moment, it offered a tantalizing possibility, a specific, large-scale anomaly that a multiverse model could potentially explain. It highlighted the kind of unexpected signature that could, in principle, act as a window into the world beyond our own bubble. The saga of the dark flow serves as a cautionary tale in the search for ultimate realities. It illustrates the exhilarating potential for discovery, but also the rigorous challenges of distinguishing a true signal from the noise at the very edge of our perception. Another dramatic blueprint for reality suggests our universe began not with an isolated bang, but with a shattering impact. The Ekpyrotic model proposes that our entire cosmos was forged in a collision between two immense parallel branes drifting through a higher dimensional space. This violent encounter concentrated an unimaginable density of energy, which then flooded our newly formed brane, manifesting as the hot, dense state we call the Big Bang. The name itself comes from the Greek word for conflagration, a fitting title for a cosmic genesis born of fire and impact. This framework offers a powerful alternative to cosmic inflation, suggesting a different catalyst for the universe's birth and, in turn, a different architecture for the multiverse. In its most compelling form, this model becomes cyclic. The same forces that drew the branes together for one collision will, after the universe expands and cools, eventually pull them back for another. This sets the stage for an endless cosmic cycle, an eternal rhythm of creation and dissolution. Each collision is a new Big Bang, followed by an epoch of expansion, and then an eventual contraction into a big crunch before the next impact resets the entire process. We could be living in just one iteration of an infinite series, our entire cosmic history, merely one chapter in a book with no beginning and no end. This cyclical multiverse is built not on an eternally inflating foam, but on a timeless, repeating dynamic. It directly confronts one of the most puzzling features of our universe, its staggering low entropy at the beginning, a state of exquisite order that seems to defy random chance. In the cyclic model, the violent smoothing action of the brane collision naturally produces this clean, uniform slate, offering an elegant solution to a profound mystery. The true test between these competing visions of Genesis lies in their unique predictions. While inflation suggests a background sea of primordial gravitational waves should ripple through the cosmos, the Ekpyrotic model predicts these waves would be far weaker, perhaps even undetectable. The collision of branes is a much smoother process than the violent quantum tumult of inflation, leaving a much fainter imprint on the fabric of space-time. This makes the ongoing hunt for these ancient gravitational waves a key battleground. Finding them would provide powerful support for inflation, while their continued absence would make the elegant, cyclical clash of worlds a far more compelling story for the birth of everything we know. A universe that lasts forever would become a very strange place indeed. Given enough time, even the most wildly improbable events are not just possible, they become inevitable. This leads to one of the most peculiar and profound puzzles in all of cosmology. In an eternal and random cosmos, the most likely observer is not a human being who evolved on a planet over billions of years. Instead, it is a disembodied brane that has spontaneously fluctuated into existence from the empty quantum vacuum, complete with a full set of false memories of a life that never actually happened. Physicists call these hypothetical entities Boltzmann branes, and they are far more than a philosophical curiosity. They represent a devastating problem for certain models of an eternal universe, including some versions of the multiverse. The logic is as unsettling as it is simple. The random, chaotic assembly of a single, self-aware brane through a quantum fluctuation is astronomically more probable than the long, orderly, and incredibly specific chain of events required to form galaxies, stars, planets, and ultimately, biological life. In a truly eternal and random reality, the number of these lone, disembodied minds should utterly swamp the number of ordinary observers like us. The fact that we are clearly not Boltzmann branes, that we are coherent beings with bodies and a consistent history in an orderly cosmos, places a powerful constraint on which cosmological models can possibly be correct. A viable theory of the multiverse cannot simply produce a vast ensemble of worlds. It must also ensure that within that ensemble, observers like us are typical, not an extreme statistical rarity. This bizarre thought experiment forces physicists to rule out models that predict an eternal, featureless future where such freak observers would eventually dominate. It acts as a cosmic sanity check, ensuring our theories of reality align with the most fundamental data point we possess, our own coherent existence. This pushes model building toward universes or multiverses with a definite beginning or a particular structure that makes our kind of orderly, embodied consciousness the expected outcome, not a fleeting anomaly in a sea of chaos. But even within the near-infinite cosmic catalog of string theory, there are rules about what can be published. every seemingly consistent set of low-energy physical laws is not guaranteed a spot in the grand library of reality. This is the critical distinction between what physicists call the landscape and the swampland. The landscape is the collection of all possible universes that can be successfully built from the fundamental strings and brains of the theory. These are the valid, self-consistent entries in the cosmic catalogue. The swampland, by contrast, is the set of all other seemingly possible universes, those whose laws look perfectly reasonable on paper but which, for deep mathematical reasons, cannot actually be constructed from the bedrock of string theory. They are impossible islands in the meta-reality, theories that are fundamentally incompatible with the underlying architecture. This is not just a philosophical classification, it is a potential master key for testing the entire framework. If our own universe, with its specific values for dark energy and the masses of particles, falls into the swampland, then the string theory landscape multiverse cannot be a correct description of nature. It would mean our cosmic address is listed in a directory of impossible places. To make this distinction concrete, researchers have proposed specific swampland criteria, clear-cut rules that any viable universe must obey. One of the most discussed criteria concerns the nature of dark energy. It suggests that the vacuum energy or dark energy in a true landscape universe cannot be perfectly constant and extremely small, as it appears to be in our cosmos. Instead, it must vary across space and time in a significant way, or be accompanied by a new light particle that has so far escaped our detection. This creates a direct and startling link between the most abstract heights of theoretical physics and the data collected by our telescopes. Our precise measurements of the universe's accelerating expansion are now a direct test for the string theory multiverse. If future observations confirm that dark energy is indeed a perfect cosmological constant, unchanging and infinitesimally small, then our universe may be stranded in the swampland, forcing a radical rethinking of this cosmic vision. This turns the vast, seemingly untestable landscape into a vulnerable hypothesis, one that could be falsified by the subtle behavior of the void itself. The search is on for the faintest trace of a drifting dark energy, a clue that would tell us whether our home resides in the valid library of realities or in the theoretical wasteland just beyond its gates. This ultimate ensemble of all possible realities pushes the very idea of a multiverse to its absolute breaking point. We are no longer contemplating a collection of cosmic bubbles or branching timelines, but a meta-universe so vast it contains every coherent mathematical structure, every potential simulated world, and every logical construct that can be conceived. This is the multiverse of all possible multiverses, a totality where every story that can be written is not just possible, but is playing out in some domain of this ultimate reality. Every variation of physical law, every imaginable form of existence, from a universe built on pure geometry to one operating like a vast, silent computer program, finds its place here. The sheer inclusivity of this vision is both its greatest strength and its most profound weakness. If everything that is logically possible must exist, then the concept of existence itself begins to feel hollow. What does it mean for our universe to be real when a near infinite number of other universes are equally real, including some where the laws of logic we take for granted are completely different? This framework struggles to make any specific prediction about the world we actually observe. When a theory asserts that every conceivable outcome happens somewhere, it becomes nearly impossible to say why our particular reality has the specific features it does. Why is the speed of light this exact value? Why do we have 3 dimensions of space? In the ultimate ensemble, there are universes where the answers are radically different, and they all exist with the same fundamental validity as our own. This represents the final frontier of multiverse speculation, a place where the quest for a complete explanation risks collapsing into a kind of philosophical silence. The idea becomes so broad that it can no longer be sharpened into a tool for making specific, testable claims about our home. The relentless forward march of time feels like the most fundamental rule of our existence. We remember the past, we anticipate the future, and we cannot turn back. This directionality, this arrow of time, is rooted in a single, powerful physical law, the relentless increase of entropy. The universe naturally progresses from states of order to states of disorder, from a pristine, structured beginning toward an eventual, featureless heat death. But why did our universe start in such an exquisitely ordered, low-entropy state to begin with? This is one of cosmology's deepest and most stubborn mysteries. Within a multiverse framework, a startling answer emerges. Our entire cosmic history, with its clear and undeniable arrow of time, might not be the default setting of reality. It could be a rare and fleeting statistical fluctuation within a far vaster and more chaotic meta-reality. Imagine a vast, calm ocean in a state of maximum disorder. Every so often, purely by random chance, a single, perfectly organized wave rises up before dissolving back into the chaos. Our universe, from the Big Bang to the present day, could be that one in a gazillion organized wave. In this view, the incredible low entropy of our beginning was not a special act of creation, but a random roll of the cosmic dice within an eternally inflating or cyclically evolving multiverse that is, on average, in a state of high entropy. This reframes our entire existence, the clear direction of time we experience, the very thing that gives our lives a narrative sequence, may be a local and deeply atypical condition. It suggests that for every cosmos like ours with a strong arrow of time, there are countless others where entropy was always high, and time has no clear direction, a bland and static soup where nothing ever really happens. This connection ties one of the most intimate aspects of our experience, the flow of time, directly to the grand architecture of the multiverse. It offers a profound, if humbling, perspective that the initial conditions we have struggled for so long to explain might simply be a matter of our own rare cosmic address. If every choice spawns a new reality, then the sting of a past regret is soothed by the existence of another you who made the better decision. This is a deeply comforting thought, yet it introduces a profound philosophical dilemma. Does the knowledge that our failures are counterbalanced in another branch of reality cheapen our victories and diminish the weight of our suffering in this one? The answer may hinge on a simple, sobering truth. The version of you reading these words is irrevocably anchored to this single thread of experience. The triumphs and hardships you face are uniquely and entirely your own, for your consciousness is bound to this narrative alone. The existence of other stories does not erase the reality of this one. In fact, it might do the opposite, intensifying the significance of the path you are actually walking. Now, expand this perspective to the cosmic scale of the inflationary multiverse. If our universe is a rare, shimmering bubble of life in an endless, sterile sea of cosmic deserts, then every living thing within it becomes exponentially more precious. The fragile dance of biology on our planet is not a common, mundane fluke, but an astonishingly rare cosmic event. This realization could fundamentally reshape our sense of responsibility, transforming our role from temporary inhabitants of a single world to conscious stewards of a near miracle. The multiverse concept delivers a powerful blow to anthropocentrism, the idea that humanity is the central fact of the cosmos. We are not the purpose of a single, tailor-made universe, but simply the inhabitants of one that happen to have the right conditions. This is a humbling demotion, yet it is also a liberation. It frees us from the burden of cosmic specialness and allows us to find meaning not in our designated importance, but in the connections we forge and the beauty we create within our own rare corner of existence. The ultimate question the multiverse poses is not about physics, but about perspective. Does living in a near-infinite reality make our individual lives feel insignificant, or does it reveal that the spark of awareness in a vast, indifferent cosmos is the most significant thing of all? Yet this grand vision of reality is not without its powerful dissenters. The multiverse has drawn sharp criticism from some of the most respected names in physics, who see it not as a breakthrough, but as a dangerous retreat from the core mission of science. Nobel laureate David Gross warns that embracing the multiverse could signal the end of fundamental physics. His concern is that if we accept a landscape of countless universes as the answer, we might stop searching for a unique, predictive theory that explains why our one universe has its specific, elegant laws. It would be like a detective faced with an infinite number of potential suspects, simply giving up on finding the one true culprit. This fear touches on a deep anxiety within the scientific community, a worry that we are trading the dream of a final, beautiful equation for a messy, untestable cosmic democracy. Paul Steinhardt, another architect of inflation, has become one of its most vocal critics. He argues that the inflationary multiverse has devolved into a theory of anything. Because it can accommodate any possible observation by inventing a universe where that observation holds true, it can never be proven wrong. If a new telescope finds a strange pattern in the cosmic background radiation, a supporter can say it is evidence of a bubble collision. If no such pattern is found, they can argue our bubble was simply never hit. A theory that explains everything, in this view, ultimately explains nothing at all. It loses its power to make specific, falsifiable predictions, which is the very engine of scientific progress. This schism is not a minor technical dispute. It is a fundamental clash over the nature of science itself. Are we courageously following the equations wherever they lead, even into the unsettling territory of infinite realities? Or are we surrendering to a comforting story that allows us to stop asking the hardest questions about our unique cosmic home? Listening to these critical voices does not diminish the wonder of the multiverse idea. It enriches our perspective, forcing us to weigh the breathtaking scope of the theory against the disciplined rigor that built modern physics in the first place. Yet the multiverse is far from the only voice in this cosmic conversation. For many scientists, invoking an infinite number of unseen realities to explain our own feels less like a solution and more like a surrender. The alternative is a quest for a deeper, more fundamental law, a single, elegant theory that uniquely predicts the constants we observe, leaving no room for random variation. In this vision, the universe is not one entry in a near-infinite catalog, but the only possible outcome of a self-consistent mathematical principle. The numbers are not tuned by chance, but locked in by necessity. This pursuit of a final theory represents the original dream of physics, a dream that the multiverse scenario seemingly abandons. Another compelling line of thought suggests our cosmos might be self-organizing or even evolutionary. Just as natural selection sculpts life from simple beginnings into complex forms, perhaps the laws of physics themselves could have evolved from a more primitive state. In the fiery chaos of the earliest moments, a form of cosmic selection might have favored stable configurations that could support long-lived structures like atoms, stars, and galaxies. Our universe's laws would then be the result of a dynamic process, not a random draw. This framework reframes fine-tuning not as a lucky accident, but as an inevitable outcome of a cosmos that complexifies over time. Of course, the apparent perfection of the constants has also reignited discussions of a cosmic designer, an idea that resides outside the methods of natural science. While this provides an intuitive answer for some, it offers no testable predictions and effectively ends the scientific line of inquiry. The true scientific weight lies with the first two alternatives, as they represent active, competing research programs with profound implications. If a unique fundamental law is discovered, the multiverse becomes an unnecessary complication. If evidence for cosmic evolution emerges, the fine-tuning problem dissolves into a historical process. The fate of the multiverse hypothesis hinges not on its own grandeur, but on the success or failure of these other paths to understanding. This is not a closed case, but a wide-open frontier where the very nature of scientific explanation is being forged in the debates of today. The search for our cosmic neighbors is no longer confined to philosophy. It is now a technological race pushing our instruments to their absolute limits. Next-generation telescopes designed to map the cosmic microwave background will scan the heavens with a sensitivity once thought impossible. Their mission is to hunt for the faintest of scars, the circular imprints or strange temperature gradients that could be the only remaining evidence of a long-ago collision with another bubble universe. This is a search for a ghostly fingerprint on the oldest light in existence. Meanwhile, deep underground in massive particle colliders, scientists are attempting to recreate the conditions of the universe's first moments. If these experiments were to discover new families of particles, like those predicted by supersymmetry, or find hints of the extra dimensions required by string theory, it would provide powerful, indirect support for the theoretical frameworks that naturally give rise to a multiverse. These are not separate quests. The immense and the infinitesimal are deeply connected. By charting the vast, three-dimensional web of galaxies and measuring the subtle evolution of dark energy over cosmic time, astronomers are gathering another form of evidence. The specific way our universe has clumped together into its large-scale structure, and the precise value and behavior of the dark energy accelerating its expansion, could reveal whether our cosmos is a unique entity or one of many. The ultimate challenge is to find a signature that can only be explained by a multiverse. A strange pattern in the CMB could be a statistical fluke. A new particle might fit into a single universe theory. The goal is to identify a prediction so unique, so distinctive, that its discovery would point irrevocably to a reality beyond our own horizon. This arduous, exhilarating process is what transforms a captivating idea into empirical science, driving innovation in both our tools and our theories as we reach for the edges of existence. The idea of infinite realities has leaped from the pages of physics journals directly into our movie theaters and comic books. These stories use the multiverse as the ultimate narrative playground, a place where a single choice can rewrite history, where heroes meet their alternate selves, and where the fate of countless worlds hangs in the balance. This cultural fascination is more than just entertainment. It is a testament to the power of these scientific ideas to capture our collective imagination. We see ourselves reflected in these tales of what could have been, exploring our own identities through the lens of countless possibilities. Yet the vibrant, interconnected worlds of fiction are a dramatic oversimplification of the scientific proposals. In most serious cosmological models, you cannot build a machine to visit another universe or have a conversation with your alternate self. These other realms are consequences of physical laws, separate cosmic domains forever beyond our reach, not destinations on a map. Recognizing this distinction is a crucial part of being an informed consumer of science. It allows us to appreciate the storytelling genius of a multiverse saga, while understanding that the real cosmic architecture is far stranger and more profound. This cultural journey highlights a beautiful synergy where the most radical ideas at the frontier of physics ignite our oldest human instincts to tell stories, to explore, and to wonder about all the paths not taken. The deepest divide in our understanding of reality is not between universes, but between two theories that describe our own. On one hand, general relativity paints a majestic picture of space and time as a smooth, curving stage where planets and stars perform their gravitational dance. On the other, quantum mechanics reveals a chaotic, probabilistic micro-world where particles pop in and out of existence and definite locations are a myth. Both theories are spectacularly successful in their own domains, yet they are fundamentally, stubbornly incompatible. The quest to unite them into a single theory of quantum gravity is the single greatest challenge in physics. It is within this profound struggle that the concept of the multiverse finds its most rigorous scientific context. The leading contenders for this unified theory, string theory, and loop quantum gravity, do not merely suggest a multiverse, they may demand it as a natural consequence of their mathematics. In string theory, the vast landscape of possible universes emerges directly from the way extra dimensions can curl up. In loop quantum gravity, a framework that reweaves the fabric of spacetime itself out of tiny, discrete loops, the Big Bang might not be a singular beginning, but a bounce from a previous cosmic phase, hinting at a cyclical multiverse. This means the multiverse is not a speculative add-on, but could be an emergent property, a feature that naturally arises when we finally solve the deepest puzzle of how the cosmos operates at its most fundamental level. Finding this theory of everything would not just tell us about the forces that govern our world, it would provide a definitive answer to the most profound question of all: is our universe a solitary masterpiece, or is it one verse in an endless cosmic poem, its structure dictated by the fundamental laws of quantum gravity? Every scientific revolution has expanded the horizon of what we can know, pushing back the shadows of ignorance. Yet the multiverse presents a different kind of frontier, one defined not by distance, but by a fundamental and perhaps permanent disconnect. If these other cosmic domains are truly sealed off from our own by an unbridgeable gulf of inflating space or the branching of quantum timelines, then they might exist in a realm forever beyond the reach of our telescopes and particle detectors. This forces us to confront a haunting possibility. Are there truths about the totality of reality that are, by their very nature, unknowable to us? Science has triumphed by investigating the observable, but here we are contemplating entities that may be intrinsically unobservable. This does not signal a failure of our methods, but it might demand a profound shift in what we accept as an explanation. When direct evidence is forever out of grasp, the weight falls more heavily on the internal beauty, consistency, and power of a theory to make sense of our own world. The ultimate justification for a multiverse may not be a photograph of another cosmos, but the simple, undeniable fact that our most successful theories of the quantum world and the cosmic dawn point toward its existence with a compelling, mathematical inevitability. We are left to wonder if the final understanding of our universe will be found not by looking outward, but by thinking ever more deeply about the elegant, self-consistent logic written into the fabric of everything. Each blueprint for reality presents a compelling yet incomplete vision. The inflationary multiverse feels almost inevitable, a natural consequence of our most successful cosmology, yet it taunts us with the promise of evidence that remains just out of reach. The many worlds interpretation cleans up the messy quantum puzzle with breathtaking elegance, but at the cost of multiplying realities beyond any possibility of direct confirmation. And the string theory landscape offers a cosmic catalogue of staggering proportions, yet its very vastness makes it difficult to pin down to the specific, tangible world we call home. The evidence we have is powerful, but it is entirely circumstantial. It is the case of the locked room mystery, where we find ourselves inside a perfectly calibrated environment and must deduce from its conditions what lies beyond the walls. The fine-tuning of the universe, the hunt for anomalies in the ancient light of creation, the strange behavior of the quantum world, these are all clues pointing toward a grander architecture. But no single clue is yet a smoking gun. This leaves the scientific community in a state of profound and creative tension. Some physicists look at the same set of facts and see a multiverse as the only logical conclusion, the inescapable outcome of our best equations. Others see a dangerous departure from the scientific method, a retreat into untestable speculation. The architecture of the multiverse is not a finished building we can walk through, but a set of competing blueprints, each with its own elegant design and its own frustrating flaws. The debate over which one, if any, represents the true nature of reality is not a sign of failure, but a testament to the vibrant, uncertain, and thrilling frontier of modern cosmology. Our journey through the multiverse leaves us not with a single answer, but with a magnificent spectrum of possibilities. Each theory, from the cosmic foam of eternal inflation to the branching paths of quantum worlds, presents a unique and compelling blueprint for reality. These are not just abstract speculations, but serious scientific frameworks that attempt to solve the deepest puzzles of our existence. They challenge us to think beyond the confines of a single cosmos and to consider a reality of unimaginable richness. The search for evidence, whether in the ancient light of the Big Bang or in the subtle behavior of fundamental particles, continues to drive innovation and discovery. This pursuit has fundamentally expanded the conversation, merging cosmology with philosophy and forcing a profound re-examination of what it even means for a theory to be scientific. The true value may lie not in which blueprint we ultimately confirm, but in the questions the journey forces us to ask. Our place in the cosmos feels both humbled and exalted, a fleeting conscious spark in a possibly infinite meta-reality, yet one capable of contemplating the whole magnificent structure. We would love to hear your thoughts. Which architectural vision of the multiverse resonates most deeply with you, and why? Share your perspective in the comments below. If these explorations of cosmic mysteries captivate you, be sure to subscribe for more journeys to the edge of understanding.